preparing to live stream. I assume we are live now on YouTube, so it's my pleasure to start another statistics seminar from Federal University of Minas Gerais. Our presenter today is Gregory Matthews. He's an associate professor in Loyola University, Chicago. He basically graduated, well, we did the whole PhD together at the University of Connecticut. And after that, he did some postdoc in University of Amherst, Massachusetts. And he moved to University of Loyola, where he is since then. And he has been working with a lot of data science, sports related stuff, and data imputation, many things like we used to do, right? So it's my great pleasure to introduce you guys to Greg. Don't mind his jokes. Usually they're not good, but he will survive. And well, Greg, you have about 15 minutes, and then, we go back to some questions or doubts on whatever you present. Thank you for accepting the invitation.
All right.
Vai pegar o meu fone, não?
All right. Can you see my screen?
Yes.
All right. So I'd like to thank Marcos for inviting me to give a talk here. I'm glad that he allowed me to come give a talk because we both went to grad school together and my grades were always a little bit better than his. So I'm glad that he's forgiven me for that and welcoming me to give a talk. It's not true. His grades are better than mine. So what I'm going to be talking about today is completion of partially observed curves using hot deck type imputation. And so let me motivate this problem. So let me explain where this came from. So this whole issue came up because I was working on an applied problem. So I want to motivate the methodological development based on where the applied problem came from. So when I started at Loyola, I met
I think your mic already switched. Your mic's gone. Wait. Oh, shit. Wait, Greg. Wait. How can I do? Jesus. I don't know how to stop his chat. He's talking there. No. You muted. Christ, let me call him. This doesn't work. You muted since this last second. We can't hear you yet. No. No sound. Nothing.
Can you hear me now?
Yes. So we basically heard the first two sentences said.
All right. Can you hear me now?
Yeah.
Okay.
Start all over again from the pics. You saying you went to Loyola and then you're basically gone.
Oh my God. Zoom. Okay. Okay.
So I'll call you if you disappear again, okay?
Yeah. When I see it, I'll just switch over.
Yeah, you know what's going on.
Okay. Sorry about this. It's a Zoom thing. I don't know how to fix it.
Still have a
what did you
problem.
hear?
Your screen is black now.
My screen's
can
black
see-
now.
Yeah, I can see the slides. Yeah. Does anyone see his screen? No screen, yeah. It's all
Oh my
black.
God.
Do you think it's better maybe for you to come out and back again?
You can't see my screen?
No, you're not sharing, right? Yes, we can see now. Okay,
You see now?
it's good, yeah.
Okay. All right. Sorry about that.
That's fine.
That'll probably happen several times. Okay. So what did you hear?
Just what I said. You move to Loyola, so it's an applied problem. You move to Loyola, gone.
Okay. So when I got to Loyola, I met this doctor named Dr. Juliette Brophy, and she is a biological anthropologist, and she's interested in studying early human behavior. One of the ways in which she's interested in studying early human behavior is through this thing called paleoenvironmental reconstruction. And the idea here is that you look at the animals that lived in the area, and then based on the environmental needs of those animals, you can understand what the environment looked like. Was there a lot of water? Was it forest? Was it grassland? And then you can reconstruct the environments. You can learn about what the early humans were doing. Ideally, what you'd be able to do is find full fossil, full skeletons of these animals. You could identify them very easily, and then you could put together a full a reconstruction of the environment. The problem is that this was, hundreds of thousands or millions of years ago, and these fossils decay, and what we're left with are isolated bovid teeth. Teeth basically are teeth are very, very strong, and they last very, very long. And most of the fossils that we observe are these teeth, and they're not even in skulls. They're usually isolated teeth. There are a few examples where you'll get a few teeth in a jawbone, but mostly these are isolated. And by bovids, I'm talking about things like antelopes. Think about antelopes and hartebeests and things like that. There's some pictures of it. I like that one in the middle because he's got some pretty sweet horns. But these are the animals that we're talking about. So there are anthropologists who they're digging for these types of fossils, and they're using these for among other things, paleoenvironmental reconstruction. So one of the when she came to me, she was interested in identifying these teeth. So they have isolated teeth. They want to be able to identify these teeth so that they can do paleoenvironmental reconstruction so they can learn about what the humans were doing. So she's interested in studying humans, and a problem related to that is identifying these isolated bovid teeth. That's where we're at. So the way these are actually classified, or there's many ways to classify these, but the way that she's interested in classifying these is by looking at the shape created by the occlusal surface of the tooth. So we're looking at, these are all molars. So if you're looking down on them, they'll have two lobes. So, they'll have at least two lobes. Some of them have two lobes. Some of them have three lobes. Think about like your molar being a little bit bigger than the other parts of your teeth. These molars are much bigger than the incisors, for instance. So you can trace around the outside of these teeth, and the shapes of these teeth are often they're very useful for classifying these teeth. So what we've done in the past is we've decomposed the shape of these teeth using something called elliptical Fourier analysis. And this is our first attempt at it, was to decompose these shapes using elliptical Fourier analysis. And then you can use the coefficients that are generated by the EFA procedure, and you can use those as features in machine learning, just standard machine learning models. Okay. I should say here, because we're doing machine learning, we have to have a training data set, and we have a training data set to train these models, but you have to have known classes. The training data set are all modern bovids where the teeth are in jaws and the tribe and species are known. So we're classifying this at two levels, the species level, which is the most granular, and then the tribe level, which is between, I think it's between class and order. Wait, that's not true. It's between it's either between class and order or genus and order in the what do they call it? Binomial nomenclature. So those are the two levels at which we're classifying. And when we do this with elliptical Fourier analysis on the outlines, we get classification rates that are, pretty high, 90% for tribe and 70% for species. And this is our first attempt at this. We were using EFA. We've now moved away from elliptical Fourier analysis because another one of my colleagues from grad school, Kartik Bharath, I ended up having a conversation with him about shapes. And he's actually, I was not a shape person, but I ended up starting to study shapes. And he happened to, completely unrelated to me, do a postdoc in statistical shape analysis. And he was like, here's how you actually should be doing it. And so we've moved away from arc length parameterization, which is used for elliptical Fourier analysis, to a square root velocity framework, which is a different framework for characterizing these shapes. And our distance measures that we need to use for these procedures, we're no longer using arc length distance measures. We're using something called an elastic metric, at least in some situations. I'll get more into that when I talk about what I'm actually talking about here. So this is with complete teeth. With complete teeth, the classifications are pretty high. So here's some results from different classification techniques. All the way to the left, you have, there's 5 techniques here. The one all the way to the left is elliptical Fourier analysis. And the other 4 on the right are when you switch from EFA to using the square root velocity framework, different classifications. And then the y-axis here is the tribe classification accuracy. The EFA is pretty good on the left, but you can see that they're either about the same or there's improvement in classifications when you're using the square root velocity framework in conjunction with this elastic metric. Okay, so basically what I'm saying here, the first whole part of this is that classification on fully observed teeth is with the shape of the occlusal surface, we can classify these pretty accurately, right? We're doing a pretty good job with classification, and we moved away from EFA to the square root velocity framework. So classification with fully observed teeth works pretty well. And here's some pictures of what these teeth look like, just to get you a sense of what it is that we're looking at. So can you see my little mouse here, Marcos?
Yes.
Okay, so the shape that we're looking at is, if you trace around this right here, that would be the shape that we're looking at. Not here, but up here. This is the shape of the occlusal surface of the tooth. So you get a closed shape. Here's an example of a tooth with 2 lobes. Here's an example of a tooth with 2 lobes and this extra third sort of like half lobe right here. These are both these are both teeth that are in jaws, and so we know what species and tribe these belong to. So while I was in one of my earliest conversations with Juliet, I said, well, these teeth must fracture occasionally, right? They're hundreds of thousands or millions of years old. You must observe parts of these teeth occasionally. And she said, yeah, we do. And so here's some examples of what this looks like. So this is a tooth right here that has been cut in half. It wasn't cut in half on purpose. It was found this way. They didn't take a full specimen and cut it in half. So this is a partially observed tooth. There would be some other part over here, but it's not observed because it is fractured. This is another example of a partially observed tooth where this is also fractured in half. Generally speaking, they could fracture anywhere, but most of the time the fracturing is occurring sort of in the middle of these teeth. So like if you look back at the full tooth, this is where the fracturing would occur. This is where the fracturing would occur. And most of the time where these teeth are breaking, it's happening there because that's sort of the weakest part of the tooth. So my dissertation work was on missing data and multiple imputation. And I just casually asked, I go, what do they do with these partially observed teeth? And Juliet said, we put them in a cardboard box and they sit in the back of the museum and no one does anything with them. So there are just boxes of these things sitting in museums, and they have no idea how to analyze these things, so they just mostly sit in boxes. They occasionally use them for some stuff, but they're not generally included in these sort of main analyses where they're looking at the full shape of the tooth. So I said, well, as a missing data person, we got to use these partially observed teeth because there's information in this. There's information in the part of the tooth. Let's try to see if we can do something about it. So I naively thought, well, we can just use existing methods for imputing shapes, and I'll just go find the R package for it. There wasn't really a tremendous amount of work done on missing data in shapes. There's some work done in like computer vision and computer vision stuff, but we kind of needed to fill in the blanks. So what we'd like to do is we'd like to include these partial shapes in our analysis, right? It's the same thing where you forget shapes for a second. When you just have a regular data set, a regular rectangular tidy data set, you don't want to throw out your missing values, right? You don't want to throw out records that have missing values in them, because the partially observed records have information in them. And this is why people have developed things like the EM algorithm, multiple imputation, all these different missing data techniques. So we want to include these partial shapes in our analysis. Juliet is specifically interested in classification, but there's other analysis that you might want to include this in, things like hypothesis testing, simple calculation of mean shapes, any other type of statistical analysis that you could do on shapes. You don't want to just throw out these partially observed shapes because they're only partially observed. There's information in them that you're removing by just removing these from the analysis. So what I started by doing is I said, let's think about what's the simplest way that I can think of to impute these teeth. And I made a connection between this approach called there's an approach called predictive mean matching in the multiple imputation literature that was developed by Rod Little in the 90s. And the idea is to match a record that is partially observed to other records that are fully observed, get a group of those, and then randomly sample from the set that is created, randomly sample the part that is not observed and fill in the missing part of the partially observed record. This is a hot deck type imputation approach. So what I proposed to do was so this is a non-parametric imputation technique, and I proposed to extend this. I proposed that we should extend this to shapes. There's a lot to know about shapes, though. You can't just naively dive into shape analysis. There's a lot of math that I wasn't considering, and so the shape people have helped me out greatly. The shape people being Sebastian Kurtik at Ohio State and Kartik Barath, who I went to UConn with, who did a postdoc with Sebastian. They've pointed me in the right direction on shapes. So the algorithm that I proposed, and they helped me work out the details, was we want to do the same thing we were doing for this predictive mean matching, but we want to do it with shapes. So here's what I proposed, and here's what we did in this analysis. So say we have a partially observed shape, and the shapes that I'm considering here are all bobbed teeth. But you could do this with other shapes if you wanted to. So consider a partially observed shape that you want to impute, and you have a collection of full shapes, right? Those are going to be used to impute the partially observed shape. What we're going to do is we're going to take the partial shape and we're going to match it to the full shapes to find a set of K donors. So we want to take that partially observed shape, and we want to say, of these fully observed shapes, which ones are the closest to that partial shape? That step is non-trivial, right? There's a lot of different things you need to think about with how do you match a partial shape to a complete shape, but this is the idea that we're going to work with. We then find some distance between that partially observed shape and the fully observed shapes, and then we create a donor set. Okay, that's the K. K here is the number of donors that we're going to have. That donor set is going to be used to randomly. That donor set is going to be used to complete this partial shape. So we take that set of K donors, and we randomly sample from that. We randomly sample from one of the K donors, and we use this as a template to complete the partial shape. Again, that part is also non-trivial, where even if you have a partially observed shape and a match, the completion of that is not completely trivial. My original idea was to before I met with the shape people, my original idea was to make this match, figure out which part of the completed tooth matched with the partial tooth, and then literally just slice off the part that was unmatched and place it on the partially observed tooth. This doesn't directly work because you want the resulting imputation to be a closed curve, like a true shape. So you have to add some restrictions about what's happening at the edges of the ends of the the partially observed tooth. You want to make them, you want to make the connection smooth. And so we're basically, I'll show a picture of what's happening here on the next slide. So this process is then repeated m times to yield m completed shapes. This is just stealing straight up from the multiple imputation literature. And so you complete the shape many times. And then just like with multiple imputation, you can, with multiple imputation, you have m completed data sets. You run your analysis on each of the m completed data sets, and then you combine across the completed data sets to come up with a final answer. All right. So that's the basic idea here. I have some pictures here of what I'm talking about. I didn't include that. So here's a picture of what I'm talking about. So the black tooth here. So let's say I came up with my, I'll explain the full details of how we're doing the matching to come up with the donor set. This is the first algorithm here, though, is about, let's say we have the matched one. We have the partial tooth and the completed tooth. They're matched, and we want to complete the tooth. This is what we called algorithm 1 in this paper. The black tooth here is the donor, and the red is the donee. So if you look up here, this red tooth right here is partially observed. That would be that would be the true partially observed tooth. Okay, what's happening here? Okay, the red tooth here is the partially observed tooth, and the black tooth here is the donor tooth. Okay, the red tooth has been matched to that part of the black tooth, right? Because we don't know, it could be, you have to figure out what the right rotation and what the right, the rotation is. You have to figure out what the translation is. You have to figure out what's the best alignment of these teeth. I'm going to explain how we do that, but basically assume that they can be aligned. What we then do is we then take the two ends of that red tooth, which is an open curve, and we want to create a closed curve because these shapes are closed. We basically close it with a straight line. So we get that blue line, and that's our initial step. Then think about this this blue curve here, or this blue line. Think about it as a rubber band. So the red curve is going to stay rigid, and that blue is going to be a rubber band, and we're going to like stretch it over that black part of the curve. And so what we're doing is we're just taking this blue part of the curve, and we're taking the unmatched part of the donor tooth, and we're going to iterate through trying to minimize the distance between that blue, that original blue straight line and the black curve. So here we have, this is at 0 iterations. After 3 iterations, we have this right here, and then we keep iterating, and it basically traces the whole tooth. And then we have, so it basically ends up tracing the whole tooth almost exactly. And then if you look at these where they're connected, it's a little bit different than the actual tooth. It has to deviate a little bit to make this actual connection. So here's one example of the tooth. This would be our final imputation. And then here's another example where this would be our final imputation. And this one, you can probably see it a little bit more clearly, that the unmatched part here, the blue curve is not completely overlapping with the black curve here because we need it to connect. We have a restriction that it has to connect to the red part of the curve. So basically, this whole algorithm is we have this red curve that is rigid, and then we're going to let this blue be like a rubber band, and we're going to stretch it over the unmatched part to create our completed imputation, right? So it's non-parametric because there's no posterior predictive distribution that we're sampling from here for the shapes. We're letting these we're letting the observed shape, or the observed unmatched shape here, complete the tooth. Okay. All right. So what we did is we did a simulation study where we wanted to see how well this would work for classification. We did a simulation study where we basically took these teeth that were fully observed and we split them in half, right? So we basically said, let's cut them in half where they would usually split. We then simulated partial teeth. We imputed them m times. We used a very, very simple classification algorithm. We used k nearest neighbors on all the imputations, and then we averaged across all the different completed data sets to get an overall predicted probability. And then we looked to see how this compared to doing classification without imputation at all. Can we just take the partially observed teeth and do classification with k nearest neighbors based entirely on the partially observed curve? Okay, so that's what we're going to compare it to in our simulation study. So Here's some example imputations with some simulated data. This right here is the black curve. Hold on, I think I'm missing a slide here. Well, I don't have the slide here, but I can explain what I wanted to put here. So I said I was going to explain how we did this matching, and I did not explain it yet. So there's two algorithms that we need to talk about. One is once you have that match, right? Once you have the match, how do you do the completion, right? And so I've sort of given you some details here. I'm not going to show you all the formulas. It's in the paper. You can go look for it yourself. But I do want to talk about how the donor set is computed, and I want to talk a little bit about distance measures. So to create this donor set, right, we need to measure the distance between we need to take the partially observed tooth and match it to a part of the completed, to every part of the completed teeth. So the first thing we need to do is there's an alignment process where you take the partially observed curve and you have to align it to all the different parts of the tooth. So you're trying to see across all the different possible alignments, what's the best section of the tooth what's the best section of the partially observed tooth that could match to this partially observed tooth. In addition to that, though, you also have to think about what's the best rotation of this tooth, what's the best translation of the tooth, what's the best scaling of the tooth, if you're interested in scaling, and what's the best reparameterization of the tooth. So you have to think about all these different sort of nuisance parameters for coming up with the best alignment, okay? Once you align, then you need to think about how do you measure the distance between the partially observed tooth and the fully observed tooth. And so what I want to give you a little bit of a detail here. We used arc length parameterization to do the alignment. So we're saying that the tooth is rigid, and we're not considering reparameterizations when we're thinking about what's the best part of the tooth to align it to. But when we measure distance, we are using an elastic metric, which allows for reparameterizations. What this basically means is in the arc length parameterization, when we're doing our alignments, when we're doing the alignment, we're saying the distance is fixed. One point matches directly to another point on the fully observed curve. That's what arc length parameterization will give you. When you move to an elastic measure, the points you can do a warping, and the points don't necessarily map the same way they would in arc length parameterization. We're allowing for we're using a warping function to change this alignment to measure distance. This allows us, if two things have very similar, like this lobe right here, or not this lobe, but this little feature right here, if that feature exists on two teeth that are matched, but it might be slightly different in the ordering of the points, arc length parameterization is not necessarily going to capture that, but with an elastic measure, you will. So we're using an elastic measure to decide what the donor set is, but we're using arc length parameterization to do the alignment, right? Not sure that's the best way to do that, but that's what we did. And so then you end up after this is these dotted points are the true tooth. We cut it in half in a simulation study. You get this right here as the partially observed simulated tooth, and these red curves right here are completions that you would get by looking at all the other teeth in the data set. The thing that I think is interesting about the reason I show this one right here is because this particular tooth has this extra third lobe. You can see in the black dotted lines, there's this true third. It's like a half third lobe. But in all the completions here, we're capturing this third lobe. It's not always lining up perfectly with it, but there's enough information in that left side of the tooth, or the black side of the tooth, that it's giving us, when we do the matching, we're getting that third lobe there, right? And so there's useful information in this partially observed tooth. And so I think this is a good example where you can see that this was matched with other teeth that had that third lobe. And so we're getting information about that other half of the tooth. So I think it's a good example. So here's some of our simulation results. So we're interested in two different scenarios in this simulation study. we're interested in, I should make the distinction between shape analysis and size and shape analysis. In shape analysis, we're only interested in the shape of the tooth. The shape being the basically the curve that's left over after removing things like rotation, translation, reparameterization, and scaling. That's what the shape is. The shape is not interested in the scale of the shape. That's pure shape analysis. In this particular setting, and not every setting you're interested in the size, but in this particular setting, we're also interested in the size and the shape. So this is the not scaling. We're removing all those other nuisance parameters, but we're not removing the scale of the tooth. We're letting, if two teeth were exactly the same shape, but one was larger than the other one, that's interesting, and that has information to the anthropologist. It has information. So here's just one quick example of all the different results we had, and this is without scaling, and this is classification accuracy of the species without scaling. So this is in our simulation study. We took the teeth, we fractured them, we simulated half of the teeth. We then tried to impute them, and then based on those imputed things, we tried to do classification at the species and tribe level. I'm just showing you species results, and this is without scaling, so we're letting size be important here. These settings over here, this M is the number of imputations, and K is the size of the donor set. And so we have, I'm showing, there was many different settings that we tried, but here are 3 settings. This is M10, K10, M20, K20, M5, K5. And the purple here is the classification accuracy with no imputations. So if you can you hear now?
Yes, we could.
Can you hear now?
Yeah.
Okay. Sorry about that. We made it.
Now it was quick. It was just before you changed the slides.
Can you see my screen now?
Yeah, everything's fine.
Okay. If
So
someone
you
knows,
were-
let me know. Can you see the screen?
Yes, we can see the screen. Yeah, it was just before you moved from this slide to the next one. You were, Hello? No, we can't hear you anymore. No audio. Greg, you're gone. Stop talking. You're gone. You're just gone. Your audio disappeared before you start talking in the slides.
Can you see me now?
Yeah, I can hear you now.
Can you see me now?
Yeah.
You hear me? Can you hear me?
Yes.
Can you see
I
my
can
screen?
No. You muted now.
Can you hear me?
Yes.
I can't hear you. Hold on. Can you hear me now?
Yes.
Okay. Can you see my screen? Can you
No.
see my screen now?
Wait. Yes.
Can you see the slide right now?
Yes.
It's a GG plot. You can see it?
Yeah.
Okay. Sorry about this, Marcos. It's my fault.
It's fine.
It's the shoddy American
This is
internet.
interesting. Yeah. We know how Americans are.
Okay, so these are the results of classification accuracy for species without scaling. So we're not considering this. We're not removing the scale. We're letting scale stay in because the size of the teeth is important here to the biologist. On the right, these different colors represent different settings where M is the number of imputations and K is the number of the size of the donor set. So here I have 20. There was other cases that we tried, but here are just a few of them. This is M20, K20, M10, K10, M5, K5. And then with purple, this is classification accuracies without the imputations. And what you can see based on this slide is we failed. If you look here, all these purple dots are classification accuracies, and they are the highest without doing any imputation. There's a few, so like here, M20, K20 beat it, and there's this one instance right here where the imputation actually outperformed by quite a bit the no imputation, but almost uniformly the purple ones win. Here's one example where it's about the same, the best one. And then I should say the x-axis here is for the different tooth types. So the first two rows here are for LM1s, that's lower molar 1, and then 1 and 2 is the left half and the right half of the tooth. And this goes through UM3, which is an upper molar, and there's 3 teeth. So there's 6 total teeth here, lower molar 1, 2, and 3, upper molar 1, 2, and 3, and then we split them both left and right, and these are the results for the species. So what I argue here is, so we basically what we're seeing here is that we're doing better without doing the imputation in terms of classification. And what I argue on this slide is, here's my argument. What I'm saying here, so when you do multiple imputation, most of the time you're doing multiple imputation because you want to estimate some standard error of something in classic multiple imputation. You want to get an accurate estimate for standard errors of your estimates. The particular analysis that Juliet, the anthropologist, was interested in here was classification. And so we kind of developed this imputation method, and then we tested it on the analysis she was interested in. And so we tested it on classification, and we're basically showing that it's not super helpful, but I think it would be super, or I think what we are doing right now is we're testing this on other traditional statistical methods, hypothesis testing, the calculation of the mean shape, things like this. So I think the important part of this paper is that we've developed this algorithm as a starting point for imputing these shapes. And it doesn't look like it's not super helpful for collaboration, but the only reason we're using classification as a way of evaluating this is because that's what this particular collaborator was interested in as an analysis, was imputation. So it's kind of a weird thing to do, is to do imputation and then classification, but that's what we were interested in. We were also developing this method. That's how we ended up here. Okay. Next slide. So my summary is classification without imputation generally outperforms imputation when classifying at the tribe level in most cases. I guess another thing I should point out is that we were using k-nearest neighbors here, and it's possible that when we use, and we're in the process of testing these things, if you're using more sophisticated machine learning algorithms, it's possible the imputation does actually help you. We don't know. And then I say here, results of classification at the species level was more mixed. There are some instances with size and shape where imputation improves classification accuracy, but it's only very few of them. So I want to show you a real life application where we actually applied this to partially observed teeth, and I want to show you what the results look like. So we took this method and we took some partially observed teeth. There weren't a ton of them at the time because well, there just wasn't a ton in the data set because the anthropologists weren't collecting these. So we have an NSF grant, and part of that NSF grant is to send the anthropologists to South Africa to go in the summer, to go to the back room, pull out those cardboard boxes and just take pictures of these things so we can extract the shapes of these. In this study, we had 7. We have 7 fractured fossil teeth, and we're gonna use this method to classify these real teeth. So these are real examples of classifications, or these are real examples of imputations that we've done for these fossil teeth. The black curve here is the partially observed tooth, and the red curves are all the different types of imputations. And you can notice again that we're just like with that simulated one, we're capturing that third lobe, and this should have a third lobe on it. The anthropologist has said, yes, that is what it should actually look like. Notice that the scale here, this is without scaling. So we're leaving the scale in the data. I believe that 300, so these are the x-axis and the y-axis are pixels, and I believe 300 pixels is an inch, just to give you an idea of how big these teeth are. So this is size and shape. If we do the same thing with shape only, so you can see that the scales now have been reduced to basically we reduce it so that the length around the curve is normalized to be 1. And so this is the shape only. We get the same kind of thing where we're capturing that third lobe in most of these, but some of these imputations are a little bit more different than the other ones that we get. But these are real imputations from real fossil teeth, and we did this for the 7 fossil teeth that we had. And those pictures that I showed you earlier were real partially observed fossils that were used in this example. So this is our results of those 7 teeth. The columns here are the 7 teeth. They're indexed by IMG and then a number. The rows here are the possible species that these could be. And if you look at the upper one here, the top one here is our species level classification with imputation. I'm sorry, without imputation, using k nearest neighbors, with k nearest neighbors with k equal to 10. When I say, I have to make a distinction here. K sub n is equal to 10. That's the number of that's the k from k nearest neighbors. It's not the same as k, the size of the donor set. Terribly confusing notation. But what you can see here is that these are the probabilities that they belong to these different species. And we're getting different probabilities here. I'm sorry, the bold numbers here are what the truth. They're basically what the anthropologist says they belong to. These are partially observed teeth. She's an expert, so she's probably correct, but we don't actually know because they're not in JAWS. So the bold here is the expert opinion of a biological anthropologist. And so these are these numbers right here are just in k nearest neighbors. You're going to end up getting the number that classified to this group divided by 10. And so all these numbers are divisible by 0.1, right? But these are the probabilities that we would classify it to that group. And so you can see for these, we're doing a pretty good job without using any imputation at all. This one we didn't get it at all. And this one we also didn't get it at all. These are the probabilities that are estimated using imputation. And we're getting similar results in a lot of cases. This one right here did way better, for instance, than this one down here. And this one also did better than this one down here. We do have a case where imputation 1. This was predicted to have 0.52 and 0.4, but largely these are very similar results. And if you had to pick a winner here, you'd probably pick the non-imputed, the non-classification without the imputation, right? So, well, you can tell I'm not overselling this method, right? I've basically shown you here's a method we developed and it works a little bit, but there's work to be done to make this useful in terms of classification. So I'm not lying to you, right? All right, so the conclusions here, Marcus, am I good on time? Yeah, pretty nailing it. So in both size and shape, the proposed hot deck type imputation procedure produces reasonable imputations. I think that's a fair statement. Reasonable in the sense that when we did the simulation study and we cut the teeth in half and we show the imputations compared to the truth, they pass the eye test. They look reasonable to me. They look reasonable to the anthropologist. We're doing a pretty decent job with this very, very simple method of completion, right? There's no distributions here that we're working with, and we're not sampling from any parametric posterior distribution or posterior predictive distribution. We're just doing really, really simple non-parametric hot deck type stuff. In terms of accuracy of classification for tribe, not using imputation in classification was almost uniformly better. And then I say here that with species, it was a little bit more mixed, but still the classification accuracy was a little bit better for not using imputation. I want to tell you about where we're going with this. We'd like to apply this method beyond teeth. So we're sort of, if anyone has any good applications where you would have partially observed shapes that are not bava teeth, holler at your boy, because I would like to know those. What we've trying to think of is in like medical imaging, are there ever cases where you take an MRI or something, but only part of the organ or something is observed? I don't know enough about medical imaging to know if there's any interesting cases there, or with an X-ray, are there partially observed X-rays? So if you have any applications that might be interesting, let me know. We'd love to apply it there. We're also interested in moving beyond classification because we'd like to show that this works, right? So what I'm working on, what I'm really interested in working on next is applying this to in hypothesis testing settings. So I'm working on some analysis where we're doing hypothesis testing to test the mean shape. Are the mean shapes, the null hypothesis, are the mean shapes equal versus are the mean shapes not equal? And one of the deciding on what hypothesis test to use with fully observed shapes is a non-trivial issue in itself. There are many different ways to think about hypothesis testing of shapes, and then to think about hypothesis testing in a framework where the shapes are also partially observed. I think it's a really interesting question, and that's sort of where I want to move next. We also I've glossed over a huge point here. In classic multiple imputation, you have the famous Rubin's combining rules, where you perform your imputation, you perform your analysis on each of the imputed data sets, and then you combine across the different imputations to get a final result. These are like classic results that are used so much no one even cites these things anymore. We need to develop combining. If we're going to use multiple imputation in shapes, we need to develop combining rules. And I naively thought when we started this, well, we can just use Rubin's combining rules. Not so. There are properties of shapes and size and shape that don't lend themselves directly to developing combining rules or just using traditional combining rules. The issue with size and shape, it's not so complicated, but with shape only, it gets really complicated because the space that the shapes exist in is nonlinear space, right? They exist on a sphere, and so you're working in the space of the shapes exist in this space where things like notions of like variance and standard error don't have direct there's no direct correspondence between what a standard error means or what a variance means in classic Euclidean space and what a variance is going to mean in this on a sphere, right? So the combining rules, developing these is not at all straightforward. I have a meeting set up with the shape people very soon to get back up on this. We sort of stopped for a while, but we're getting back into that part of it. And also, along with my work on the non-parametric side of things, there is a graduate student at Ohio State right now who is working on developing a fully parametric Bayesian model for imputing the teeth. And they're interested in doing the imputation and the classification all in one algorithm. So I've sort of separated the imputation and the classification, but they're going to try to do it. They're developing methods to do this all together, right? I think that's all I have to say. Here's some fancy NSF grant numbers. And these are my collaborators. Sebastian and Kartik are both the shape people. Sebastian's at Ohio State, Kartik's at University of Nottingham, and he went to UConn with me and Marcos. I think Kartik was probably a year behind us, but yes. Guy can do math. Juliet is the anthropologist. Ofer is my advisor from UConn. He's the missing data person who just helps advise us on missing data issues. And George is our computing guy at Loyola. The last thing I'd like to say is if you look at this second citation right here, we've released a reference database of these teeth. So these are completely publicly available. If you're interested in a shape data set, we have the black and white images so that the edges can be extracted very easily, and you can get at these shapes. So if you're interested in a publicly available shape data set, there is one. There's one for you. That is all I really have to say.
Thank you, Greg. Thank you. So very interesting. I would just open for questions from the audience to see if they have any. If not, I have a few questions myself, but let's see if anyone wants to ask anything or make a comment or anything. So people, if you, I think I did the unmute themselves.
I just
Let
see
me allow
attend. It looks like people are just writing their names and
Yeah, I asked them because they need to write it down so I know who are here because this is kind of a discipline, so I need to know
I
who's.
see.
I don't want to be counted. But anyways, let me ask if you feel like just open your mic and ask, okay? First, I was thinking, what is a mean or median shape value? It's a weird thing to think at, right?
Oh, it's very strange. So I asked the same exact question in one of my very early meetings with the shape people. And so if you think about the idea, the way they explained it to me was, if you think about the idea of what is a sample mean in traditional statistics, you add everything up, you divide by n, right? That's a sample mean. The way you get a sample mean, or one of the ways of deriving a sample mean, is that the sample mean minimizes the squared distances from, if you think about measuring the distance between all the observations in your data set and X bar, the mean minimizes the squared distances, right?
Mhm.
So in Euclidean geometry, you're just dealing with like regular distances where you're subtracting them and you're squaring them and you're minimizing squared distances. You can do the same. You have the same kind of idea where you can define a mean shape as the shape that minimizes the squared distances between your collection of shapes and this mean. What this means, though, is that you need to come up with a distance measure that works in the space that you're in, right? And so depending on what type of distance measure you choose, you can get actually different means. There's something called, so the one that we're using is something called a Karcher mean, where you can Google it. So it's called the Karcher mean, and the idea here is that you're minimizing the squared deviations from the mean to all the different shapes in the data set, right? And so in the same way, you could also define a median. But this depends on your choice of distance, and you need to make a good choice for that distance, because in size and shape space, which is linear, the size and shape space is basically RP, whatever dimension you're in. The shape only stuff exists on a sphere, and the distances in that space they don't get strange, but they are not what you think of as classic statistics, where everything is rectangular and in Euclidean space. But as long as you choose the right distance, or you choose a reasonable distance measure, that's how you're getting at a notion of mean and median.
Yeah, interesting. Because I never thought the mean as, you're right? It's the minimizing of some objective function, and then if you define
I was
that
like,
way, then you can just do it whatever you feel like. Yeah.
right. It's a great
Otavio,
explanation.
Otavio has a question. The true complete shape is a donor option in the simulation, or you remove the, right?
It had to be removed, right? That's a great point. So when we first ran this, so what they're saying, I believe, is when you do the simulation study and you take tooth 1 and you chop it in half, and you're finding the set of teeth for it, you don't want to include the complete tooth 1 in the potential donor set, because it would match perfectly. I will tell you that when we ran the code the first time, we were super excited because we were nailing it, but then we were like, oh, we didn't remove that tooth. So we did. You have to remove the tooth in the simulation study. Absolutely. So the results are, it is removed.
Okay,
Great point.
I have a question here. I think it's so very nice intuition, right? I have partial tooth. I will imputate the other half, say, and I will use the knowledge I have from the partial tooth. I will impute this value, and intuitively, at least for me, it should improve my prediction as well.
Mm-hmm.
And then suddenly you show results that, throw them away, put them in the box, leave them at the museum. It seems for the classification problem, not other problems, it seems to be in the box is kind of the best you can do, which is very counterintuitive for me, which is annoying. So I was thinking, where is the flaw, right? What's going on? What could be going on in the imputation that makes your results to get worse? Because even though, okay, you say imputation is for measuring standard, who cares? I'm putting a tooth there. If that, and that's another thing. You show to specialists, they say, oh, this is a nice imputation. It makes sense. This tooth is, it makes sense. If I look at this, I'll probably be able to, so give them two teeth. And one is the true one, the other one is imputed, but you don't tell them and say, tell me which one is the true one based on, do that many times and see if they're able to differentiate them, the specialists. If they're not able to differentiate them, it's just saying, for humans, there's no difference in this information. But for the computer, clearly, there's a huge difference. Kind of maybe you putting a tooth from a different species to complete the original one, and it's mixing it up. I don't know.
It's possible. So I guess so because the main goal of this work was to develop the imputation method, we were like, let's just do the simplest thing we can think of for the classification algorithm, and we used k-nearest neighbors. I think that, well, I don't know if I think this, but I would like to test at some point using a more complicated or a more sophisticated machine learning algorithm. I guess to your question though, why do I think this is happening? My guess is that if you're already doing, if you're doing the alignment, right? If you're doing the alignment already, basically the classification of that, the purple dots, that's being done. You're basically doing the whole first step of the imputation, right? So you're saying, what's the best match to this? What is the best rotation? What's the best translation? You've already done that. And what these results are showing is that basically by just doing that, you're getting better results in doing the imputation. And so I guess my intuition behind it would be that the imputation is kind of adding noise, right? But when you're calculating variances and uncertainty, you want to accurately capture that noise. So that's why I think it's not necessarily working for classification, but I think it would be useful for more traditional statistical techniques. Do you buy that answer, Marcos?
I don't know. You show me in the future. I think so. My next question was, you showed some very nice classification for, species and so on. You use standard but more advanced machine learning. I was wondering if the KNN is the problem. It's too simplistic, and basically you cannot observe information to differentiate the tooth itself, because even the classifications are really bad all over, right? It's better with the, so if you can go from 40% to I don't know 70%, that's what you previously showed. Maybe that method can learn to differentiate when you impute as well. Then in the KNN is not doing that. I don't know.
Yeah,
Good luck
I mean,
with that.
I think we have to try more sophisticated methods, and we are. So the slides that I showed, do we have to go? I'm going to go when I stop talking?
No, you're good.
Okay. The slides I showed at the very, very beginning. So this work is sort of like 2 papers ago. The most recent paper was let's figure out with completed teeth how we want to do this classification. And so we did it with we're fully in the squirt velocity framework. We're working fully with the elastic metric when we're measuring distances, and we're comparing things like support vector machines, neural networks, random forests. We're using those as our classifiers. And the way we're generating features is by projecting the shapes onto a tangent space. So in shape world, we're on this sphere, and we can't do traditional machine learning stuff with that. So what we do is we find the mean shape, which is going to act as the point which we're going to create the tangent space based off of. We then create a tangent space at that point and project the shapes onto that tangent space, which is now a linear manifold. And then when we're in that space, we can do whatever we want to do. We can do random forests, all the traditional machine learning algorithms. We haven't done any of that with the partially observed stuff. So what we'd like to try is do the imputations, take the imputations, project the imputations onto the tangent space to create features, and then use those features to do the classification.
I see. Because so
That has not been done yet, no.
you for functional data analysis, your case is worse than functional data analysis because shape has to start and finish at the same point and so on. Right?
It's a
Not
subset.
only a function.
It's a subset of function. It's a functional analysis with a restriction that the start and end point have to be the same.
Yeah. So can you use like functional PCAs to get your features? Will that work? Because I see many people doing that for functional analysis to get the function to transform in some features. Who knows which one? And then they will just
Can
run
you see my
this.
screen?
Yeah, yeah.
So if you look here, the methods that we tried, this is elliptical Fourier analysis. These two over here, these are based on functional PCs. So these were, we based the classification on the principal components of the projected features onto the tangent space. And this is the reason this is useful is because in these ones right here, the dimension is hundreds, right? We have hundreds of, we're working with hundreds of dimensions. If you can project down to principal components, you're reducing your dimension. If you can get basically the same level of accuracy, but you're working with the principal components, there's a benefit to that. So we were looking at principal component analysis to generate features, and it looks like in most cases it's a little bit worse, but not much.
I see. Okay, so we can talk later. I don't have any more questions. Anyone else? Let me see. I think no questions in chat. So thank you, Greg, again for your time. Go for lunch, and hopefully we can see your future talks when you find a solution to this. I'm sure you're going to find some solution at some point. And it's good to show the students how research is as well, right? Because sometimes they're frustrated that things doesn't work. And that's, I would say, 80–90% of the times how it goes. Until you find a nice solution, it doesn't work many times before that. So
yeah, I mean, with this particular paper, I think the development of the algorithm.
Your sound is muted now. When I say, yeah, now you're back.
Okay, there we go. We're back. I'm back.
Yeah, you're back.
All right. We only lost it twice or something so. Good to go. All right, Marcos, are you going to be in the United States anytime soon?
Probably next year, December. That's the closest I know.
December 24?
Yeah. That's the closest I know because I'm going to IBC, I hope.
Okay. Where's that?
Atlanta.
What's IBC?
Biomedical Society Conference.
I'll go.
It's fun. Well, I never been to one though. Yeah. Just search for it. It was supposed to be in Buenos Aires, but I just got an email saying they moved to Atlanta. So
okay.
I assume I'll go. Okay, so the students are all good to go. Thank you, Greg, for your time. And it was my pleasure. We keep in touch. Do you use WhatsApp at all, by any chance?
You know the only person I use WhatsApp with is Kartik.
Oh, really? Great.
Yeah.
So maybe I'll start chatting you there. It's much easier, right?
Yeah.
Emails